Okay, welcome back everyone. So in this video we're going to be talking about the concept behind conservation of energy. Conservation of energy is one of several conservation laws that you're going to learn about. You might have already learned about the first in chemistry, conservation of mass, which is basically a way of saying that, okay, if you have some things that go into a chemical reaction, that whatever the stuff is you put in has to come out. So it can be in a different form, but the total amount of mass is going to stay constant. Well, conservation of energy is kind of a similar thing, and what we say for it, at least the definition that my book uses, is that the total energy of an isolated system is always conserved. Okay, so let's break that down. What does that mean? Okay, first of all, total energy. When we talk about total energy, we're usually just talking about mechanical energy, but that can also include energy lost to friction in the form of heat. Now, when we actually do things with conservation of energy, we're only going to be looking at mechanical energy. And so mechanical energy is written as the sum of kinetic energy plus potential. And it's important to understand that kinetic can come in different forms. Later on, you might learn about rotational kinetic energy, but the one that we're used to, the 1/2 mv squared, is what we call translational. So there's different types of kinetic energies. Then you can also have different types of potential energies. You could have potential energy due to gravity, potential energy due to a spring, potential energy due to an electric force, and so on and so forth. So you have to carefully look at a system and decide what makes up my system and what kind of energy is present. So there's a lot of problems about roller coasters. So there's a roller coaster and a couple hills, and as the roller coaster goes along and goes up and down the hills, what kind of energy is present? Well, there's no springs hanging out, so there's no potential energy due to springs. There's just going to be potential energy due to gravity. It's going to be moving, so there's kinetic energy due to translation, and that's our 1/2 mv squared. And again, potential energy due to gravity is mgh. There's no electric forces or anything else weird going on, so in an example like this, we would just say the total energy is potential from gravity and kinetic from motion. So it's important to keep in mind that you can have different forms. One quick warning about conservation of energy is that when we use it, we usually only talk about cases where there's no friction. So here's a warning. Well, first of all, let's state what conservation of energy is, equation-wise. Conservation of energy says that if the total energy of a system is always conserved, that means that the total energy that we start with initially will be equal to the total energy at another time. Okay, so this could be the total energy maybe at the top of the hill, or the total energy at the bottom of this hill, or somewhere in between. No matter what, the total energy, the potential energy initial plus kinetic, will be equal to final potential plus final kinetic. So notice that there's nowhere for friction in this equation. Your teacher might show you an alternate version of this which includes friction, and I'll show another video on that a little bit later. But when there's no friction, this is an extremely useful equation to use. One last thing. When there is friction, I like to use the work kinetic energy theorem. So that one at least makes more sense in my head, but one of the nice things about energy and work is that there's several ways to solve problems, and you can use what works for you.